Okay, so this is our last lesson for calculus. We're going to be looking at solids called either solids of revolution or volumes of revolution. Okay, so how do we do this? How do we get a three-dimensional shape mathematically? It's actually very easy. You start with a plane shape, like this triangle here, okay, which is just flat, and then you simply spin it, and it becomes a three-dimensional cone. Okay, so there's a relationship here between the area of our, when you spin it, you get the cross-section is going to be a circle. So the area of a circle is pi r squared. And if we take little thin slices through our solid, then we're dealing with volume, which is what we're interested in. And the formula for volume, you'll remember, is essentially it's exactly the same as the area of the cross-section, so the area of the circle times the height of the cylinder. So this is what we're going to be doing. We're going to be calculating volume of areas underneath the curve that we're spinning, but we're only going to be doing this around the x-axis. Right, so let's look at some details. Okay, so it's actually very similar to what we were doing when we were calculating the area of under the curve. If we make, remember the theory of this was if we made these tiny wee slices underneath the area of the curve, then we can calculate the area of the slice, and the area, total area under the curve will be, you add up all the little slices. And of course what we did is we used calculus to make the width of the slices get closer and closer to zero, so the number of slices gets closer and closer to infinity, and we end up with, instead of just an approximation of area, we end up with an accurate area of the area underneath the curve. Now what's going to happen is we're going to take this small slice and we are going to spin it. Now what happens when we spin it is that it turns into a disc, a circular disc that is that has a radius of the actual y value, or where the function is above the x-axis, so the y value of the curve, and the width of our disk, and you can see that down here, the width of the disk is just that small area of the x-axis that we made the slice through. So this little disc is like a little skinny cylinder, so we use the formula for a cylinder. Now, so the formula for a cylinder or the disc is the volume is equal to pi times the radius squared. Well, the radius, as I've already said, is actually just this length here, the y value underneath the curve. So we can substitute for r the f of x. So the volume becomes pi times f of x squared times the small height, or the delta x of the thickness of the actual volume of the actual disk. Now we put all those disks together and we make the thickness of the disks closer and closer and closer together, and we end up with an actual formula for the accurately calculating the volume of revolution, which is given by volume is equal to pi times the integral between the two limits of y squared, or f of x squared, with respect to x. Now this formula is in your booklet, so you don't need to remember it. Okay, so let's try an actual question. Okay, so the curve y equals square root x minus 1, and we want to find the volume of this between 1 and 5. So first of all, we're just going to sketch this. this. Okay, and it's a square root graph that's been moved to the right by 1 unit. So it's going to look something like this, a parabola on its side. And our limits are where it touches the x-axis, which is at 1, and at x equals to 5. So up until now, we've been finding the area underneath the curve with definite integration, and now really it's just exactly the same thing, except that we're spinning the shape. So we need to draw something that looks like a reflection. It's not very good, and we end up with a kind of like the tip of a finger, a little cone-shaped, three-dimensional object. Okay, so the area, the orange area underneath the curve, is equal to, okay, the integral, the definite integral between 1, the lower boundary, and 5, the upper boundary of our function, which is the square root x minus 1, and the whole thing has been integrated with respect to x. Okay, to turn this into volume, the formula doesn't change very much actually. We just, the volume of the shape is going to be equal to, well, first of all, the area gets turned into a circle, so that's where the pi comes in, and pi is a constant, so we keep that out the front of our integration sign. So the integral of 1 and 5, the square root of x minus 1 with respect to x. Oh, and we need to square this. Okay, so not a huge difference between the two formulas. So let's just go ahead and calculate this. So the pi is going to stay out the front until the end, and what we're going to do here is we are first of all going to square our function. So I'll just rewrite it this way. We've got the upper and lower boundaries here, and of course the square of a square root, they just cancel out, so our function is x minus 1 with respect to x. Okay, so now we can take the definite integral. So pi continues to stay out the front. We do our square brackets, and now we need to integrate, so x is going to become a half x squared minus, and 1 of course is going to be x, and our boundaries are 1 and 5. Okay, so now we just need to substitute. So still keeping pi out the front. Okay, we'll substitute the upper boundary first, so we have a half times 5 squared, so that's going to be 25 over 2 minus 5, and then we subtract the lower boundary, so half of 1 is just a half minus 1. Okay, so this gives us pi. Okay, 5 is 10 over 2, so we have 25 over 2 minus 10 over 2, it's going to be 15 over 2 minus, and we've got a half minus 1 is negative a half. And so what we end up with is pi 10 over 2 plus a half is 16 over 2, which is 8. So we've got 8 times pi units cubed, because now we're talking about volume. Okay, so that's relatively straightforward. Okay, now we're going to try one more question. This one is not in your handout, and but it's an extension question similar to the types of questions that we were doing when we're finding the area between two curves, because that's what we have here. We've got two curves, y equals square root of x and y equals x cubed. Now, to do a question like this, you are going to have to first of all find the roots, like where this graph is going to cut the x-axis. So we do that by making 0 equal to square root x, square both sides, and of course we get x is equal to 0. Do the same thing for the second function. 0 is equal to the square root of x cubed. Take square both sides, and once again we just end up with x equals 0. So both functions start at 0. That's the only place that they cut the x-axis. Okay, and the next thing we need to do is we need to find where these two curves intersect each other. So to do that, we're just going to make the two curves equal to each other and solve. Now, the reality is, unless you've got a very, very simple couple of functions like this, it's probably going to be a calculator question. Okay, so we've got x squared both sides is equal to x cubed, and of course the solutions here are x is equal to 0, we've already got that, and x is equal to 1. So let's sketch this and see what it looks like. It's quite different from our last looking curve. Okay, let's choose this color for our y equals square root of x. This kind of looks like this. Y equals square root of x. And choose another color for the other curve, which is y equals the square root of x cubed. Okay, and the point where they intersect, of course, is at 1, and they intersect again here at 0. So the area we're interested in is this area here, and when we spin this, we will get a, it will be reflected in the x-axis. It's going to look something like this. And our slice, you can see that when we slice through, there's a big hole in the middle. So what this actually looks like, if we were to take that slice out, it would be a circle with a hole in the middle. So the whole shape actually looks something like a cup or a bowl, and we call this, instead of a disc, we call it a washer. Yeah, those of you who have ever looked into a tap, you'll know what a washer is. Okay, so let's find the volume of the shape. The volume is going to be pi times the integral. Now, it's just like when we were finding the area between two shapes, we need to identify the top shape. So we'll call this the top function. So that's y2, and that has to be squared, minus the bottom function, which we'll call y1, that is also squared with respect to x. Okay, so let's substitute into our function. We're going to keep pi on the outside, and we are integrating between our lower limit is 0, our upper limit is 1. Now our top function is y equals the square root of x. So we have the square root of x, and that has to be squared, minus the bottom function is the pink line, y equals square root of x cubed. And that's also squared with respect to x. Okay, so we'll simplify this by squaring our functions. Pi stays on the outside. So 1 and 0 are our limits. Square root of x squared is just x. And it's going to be minus x cubed. And the whole thing is with respect to x. Okay, so now we can take the definite integral of this. So still we keep pi out on the outside, so it's just a constant. And now we need to integrate x. It's going to be a half x squared. And it's going to be minus x cubed is going to become a quarter x to the power 4. Square brackets, and we're doing this between 0 and 1. Okay, so now we need to substitute our values in. Pi will continue to stay at the front, and we substitute the upper one first, which is 1, so we've got a half times 1, so it's just a half, minus a quarter times 1, and then we substitute the lower limit, and it's just everything there is going to be 0. Okay, so what we get is a half is 2 quarters, so we've got a pi times 2 quarters minus 1 quarter, which is a quarter. So it's just a quarter pi, so our final answer is pi over 4 units cubed.